So no, this is about why you shouldn't automatically try to optimize away virtual functions. There's the obligatory slide number 2 about who I am. I figured the audience here is divided according to this Venn diagram to people who already know and people who don't care. So I won't bother you with that one. But I do want to talk about virtual functions, which seems to be the dominant sentiment about. People either don't want to use them or they apologize for using them. And I want to frame the discussion before I start. You're getting a problem, and this problem requires a design. And sometimes the natural, for some definition of natural, design you would choose is based on virtual functions and inheritance. I am only talking about those cases. I am not talking about the cases where the natural design does not involve inheritance. I'm not trying to convince you to use inheritance but everywhere. That's not the talk. The talk is about the cases where you say, I'd use inheritance, but virtual functions are slow. And I'm trying to convince you not to do that. So, yeah, let's benchmark, right? That's the obvious way to test that, right? So we define a base class, which is not really a base class. It's the only class we define in the entire program. And our benchmark gets the pointer to the base class, so it doesn't know what it's getting. It doesn't know that this is the only class in the whole program. And it starts the clock, tests a certain number of iterations by calling the concrete version, this one. And then, it stops the clock and it saves the duration. And then it starts the clock again, spend the same number of iterations calling the virtual function, which there's just one implementation, but it doesn't know that, and stop the clock, and then we compare how long each took. How many here think the virtual function will take, I don't know, over 50% longer than the concrete function? How many people think it will take around 10% longer? How many people think it will be within the error margin the same? How many people would say that the virtual function will be within 10% faster?
How much work? How much work is each function? What does the function do?
Nothing. It just says return 7. How many people think that it will be 50% faster? Nobody. Okay, let's try running it. So I called it benchmark 0. And it says that virtual functions are 2% faster. Let's try running again. 42% faster, 54% faster. I think we got it wrong. And just to make sure I make my point clear, I wasn't expecting those results. I spent most of yesterday with a couple of attendees who are experts in this domain, trying to figure out why that happened. And I don't know. Now, the thing is, when I submitted the talk, one of the reviewers said they wanted to see deep assembly profiling. And I wasn't planning on doing that. I wasn't planning on doing that because I think it doesn't matter. You put source code from one end, you get the ultimate blob on the other. It does what you ask for, you don't care how, and the only thing you care about is what the performance is. But when you get something so unexpected, I did go into the assembly to make sure one thing. I went into the assembly to make sure that the concrete function indeed has a concrete call, and the virtual function indeed has an indirect call. I wanted to make sure that the optimizer didn't get away with it. And you know, I had to put the definition in a separate file so the optimizer won't figure out that the functions don't do anything and devirtualize the whole thing. Which means that this benchmark is all sorts of meaningless, right? It's meaningless because I disabled the optimizer, which is precisely what you don't want to do with your code. It's meaningless because, okay, we got a result, we don't understand it. And I don't mean that rhetorically, I don't understand the result. But what are you going to do with it? What does it mean for whatever program you're going to write? Not clear. And also it's meaningless because the premise is wrong. The concrete function call isn't the same, doesn't do the same thing as the virtual function call. The concrete function call calls a certain function. The virtual function call is a customization point. You wouldn't use them under the same circumstances. So even if the virtual function call was slower, like everybody in the room, myself included, expected, that doesn't mean you shouldn't use them. So let's try something else. What's that? A benchmark. But you know, I'm trying to do a more meaningful benchmark. So I decided to take a real use case I had to use myself. I won't go into all the details, but the really gist of it is there's some input data, source code, as so it were. In that particular case, it was regular expressions. You pre-process it in one process, and then you serialize the result, and then you deploy or use that result in a different process. So that's the idea. And the challenge here is that depending on the pre-processing step, there is more than one efficient way to serialize the results. So the file I'm creating, its format depends on what happened during the pre-processing step. So the runtime part has to have multiple implementations. So that's what the benchmark does. It gets a file, and then it has two ways to decide how, based on runtime parameter, it decides on one or two implementations, and it picks between them in two forms. One is a base class with a virtual function, and the other is by template expansion. So I expanded the actual processing into a template, and I expanded twice, once processing this type of file and one processing this type of file. How does it go? Well, let's see. I don't think it's built, by the way. So we need to give it the file that, let's give it the, permission denied, sorry. Sorry about that. So the virtual ran 78% slower, 14% slower, 35% slower, 18% slower. Now, I will point out that while this benchmark is based on a real use case, it's still kind of meaningless. Because if you think about it, this benchmark has the best case scenario for the concrete case, right? We do one if at the very beginning of the program, and then the rest of the program runs as if that was the only option. So all of the caches are tuned to no customization at all. Whereas the virtual case still has to do the indirection every call. So this is another benchmark that is kind of meaningless. There is the trend here that I'm trying to pass through, that benchmarks are all meaningless. But then again, yeah, this is more in line with what we expect, right? Except a bit of trivia about myself. I have a YouTube channel. And to edit video, I need a beefier computer than this and a better graphic card. So I try to run the same benchmark on that computer. And the results were the opposite. Virtual functions ran faster. Which is alarming in terms of if you think benchmarks mean anything, because it means that the same source code compiled with the same compiler can run with significantly different performance profile based on whether you're running it on an Intel laptop or an AMD desktop. That's troubling. Because if we want to say something very concrete and certain, saying virtual functions are slower, and the answer is, yeah, but it depends on the hardware you end up running it on, and the compilation flags, and the compiler version, then maybe that sentence doesn't hold as much weight as we think it does. Just for reference, these are the two CPUs involved. That's the CPU for my laptop, and that's the CPU for my desktop. I don't have any meaningful insights to gather from that information. So let's take things to the extreme. Another benchmark, because the first two went so well. This time what I'm doing is I'm essentially picking up a certain amount of function calls. So let's say 16. And the function calls are picked from a set of a certain option and randomly placed in an array. So for the virtual function calls, that's just instantiating one of the 32 base classes based on a random number. And for the concrete function call, that's just an enum saying which one to call. And then I go over a loop of calling these n calls a certain amount of time. And I ran that repeatedly so that the number of different functions I'm calling times the number of repetitions more or less remains the same, around 16 million. And I can draw that in a graph. So this graph tells us the slowdown caused by virtual functions. So how much slower were the virtual function calls compared to the concrete function calls. And from this graph, we can deduce absolutely nothing. But it gets better if instead of just doing the division, I use the base information. So this is the runtime for, the blue is the virtual, and the orangey red is the concrete version for how many different functions there were. So the more variations I have, the more to the right. And remember, the total number is always the same, so if the numbers go up, it means the total execution was slower. And we see that, indeed, virtual functions are, for the most part, except for some outliers, slower. But I would point out that you wouldn't want to be in this area anyways, right? This is a horrible place to be. We started out at around 250 milliseconds for the 16 million calls. And by this point, we're at over almost 1.2 seconds. So it's a horrible slowdown for both cases. That's why the previous graph was so meaningless, because it didn't show us that. And what this tells us is that the CPU has caches. And what the flattening of the curve means we've exhausted the cache, we're no longer getting any more useful help from the CPU, and we're just running on the bare metal, and that's 6 times as slow as with a cache fully activated. But wait, I have another computer. That was on my desktop. What happens on my laptop? This is the graph. It superficially looks the same, except what you'll notice is that the numbers start negative, and the peak is much later. It's 500, whereas before it was at around 150. And this is the actual graph, and we see that virtual function calls are actually faster both when the caches are fully deployed and when the caches are fully depleted. And in the middle, the concrete version is faster, which tells me that the cache employed for optimizing virtual function calls is smaller than the cache deployed for optimizing concrete calls. By the way, if I understand correctly, it's a pure guesswork because I haven't found any documentation, but if I understand correctly how the caching is done, that's actually a requirement because every indirect call cache needs an entry in the standard call, in the standard branch prediction cache to refer to it. So, conclusions. I don't know. Relevant factors, everything, right? I mean, so far we have not been able to find a factor that isn't relevant. Even if you compare the first benchmark I did with the last benchmark I did, the first benchmark I did ran faster on the AMD, the virtual functions ran faster on the AMD, sorry, the first benchmark I did, the virtual functions ran faster on my laptop, on the Intel, and the last benchmark, the virtual functions ran faster on the AMD. I've had cases where switching from GCC, so I compiled with GCC, and the virtual functions were faster on the Intel and slower on the AMD. And then I'd compiled the same code with CLang, and the virtual functions, and they both reversed. So far, my main conclusion is that benchmarks are meaningless because you pick up something to test, and that something dictates the result, and that result may not apply to anything else that will be relevant. And it turns out, when I first found that out, I felt like, wait, but everybody knows, right? I must have an error in the benchmarks or something. But then I found out I'm not alone. I encourage you to grab the slides once they go up and check out this Stack Overflow page. The guy says, I'm trying to figure out why virtual functions are faster. And he writes a benchmark. And then he goes through, he left it in the Stack Overflow, I think it was a question. He left the iterations he did. Wait, there was a problem with the benchmark here, there was a problem with the benchmark here. This is from the last iteration. Essentially, he says, it was comparing virtual functions to std variant. It says, okay, get if and hold alternatives are best, except for on CLang, virtual seems best, which is strange because I remember it being best on running better on GCC, which is exactly what I've been seeing. For some programs, GCC is better. For some programs, CLang is better. And std_visit is always worst, which goes I want everyone who is wishing to replace virtual functions with variant to keep that point in mind. Do not assume that just because you don't see with your eyes virtual function calls, that there are no virtual function calls, because a switch case, which is what std visit is, will sometimes get optimized to an indirect call, which is a virtual function call. And B, because don't assume. But let's say the common wisdom is correct. Does it even matter? So I'll tell another tidbit about myself, okay? I used to work for a company called Weka.io. Weka is producing software-defined storage, which means we write code, I'm not there anymore. We wrote code that was supposed to have the same performance characteristics as a locally connected NVMe drive. The unit of measurement, so if I made a change, the level and that change affected performance, I would come see the chief architect would come see me if the performance change was more than 100 nanoseconds. So that was the unit with which we measured performance. And then I switched to a company called DriveU Auto. DriveU is doing remote control cars, except when I say cars, I mean full size, drive on the road with people in it. And when I say remote, I mean several hundred miles. So essentially, that's you stream video from the car to a driving center, which then inputs commands and send them back to the car. It's supposed to be an augmented technology to autonomous cars so that if they get stuck, a remote operator can release them. And when I joined, obviously, people's lives are at stake, right? And it has to be exceedingly low latency. When I joined there, they told me, look, we are extremely latency sensitive. Every millisecond counts. Millisecond? Oh. Wait, so I can dynamically allocate in memory? I can do system calls. Whoa, endless possibilities. So the thing is, okay, let's say virtual functions are slower. Does it matter for your use case? Because if it doesn't, and remember, I want to draw you back to the original framing. We're only talking about the cases where you'd want to use an inheritance-based design. Which means that by definition, if you're not using an inheritance-based design because virtual functions are slow, you pay a cost right there and then. You're using you're not using your best design for the job. So let's try and draw some conclusions anyway. First of all, I hope I managed to convince you that the virtual functions are slower is flat out wrong. I'm not saying virtual functions are faster, but I'm saying automatically saying virtual functions are slower just doesn't cut it. And I will say that some of the alternatives people automatically go to are consistently slower. Another thing is benchmarks are meaningless. Don't benchmark. Do profile. Okay? Do take your code, the way it's supposed to run. You're still benchmarking in that you're picking hardware to work on. But it is meaningless, but it's unavoidable. And profile your code. Now, that doesn't apply to, say you're hypothetically, hey, how are you doing? You're a compiler developer, and you want to test the performance of the code you generate. So you pick a benchmark of programs to compile and measure those. It is a benchmark, it is meaningless, but again, it's kind of unavoidable. You have to pick something. But wherever possible, try not to benchmark, i.e. pick something out of its context and test it individually, but profile, test it in context. And of course, use the best design you can. I will point out that when I advertised this talk on LinkedIn, someone approached me and said, no, I'll give you a counterexample. Silang recently posted a blogger post that said that they took a benchmark cases and enhanced their devirtualization support and saw an average improvement of 0.8%. Now, when I say that people laugh at 0.8%, do not laugh at 0.8%. An average 0.8% means that some program gets accelerated, but much, much more. But what I do want to point out is that this isn't a counter example. It's a supporting example. It means that I wrote the same code I intended to write using the design I chose, which was my preferred design. And now, because the compiler got better, the cost I paid for choosing the best design in terms of software maintenance was reduced. That's not a counterpoint. And the main point here is that this isn't a period, it isn't an exclamation mark. By all means, I think the discussion here should begin. It's not where it should end. So by all means, talk to me. Questions? No questions? That would be really, really strange.
Hi, that's an interesting talk. Thank you very much. I wonder if you maybe overlooked one of the reasons you might use a variant in the first place. This is definitely why I would tend to prefer them, is one of correctness. I prefer to use variants in...
Let me stop you for a second, okay? If the design says that a variant is the best solution for what you're trying to do, by all means, use it. Don't rely on some schmuck on the stage that tells you it's slower. Use it, profile. If it's fast enough, there you go.
Fair enough.
Thank you for that talk. I wholly agree with the idea that we can't trust benchmarks and we have to really profile and really think about what's going on. Now, my question is, last year, there was a talk where they talked about the cost of virtual functions and how the true cost was the loss of the inlining. I wanted to ask, to what extent did your benchmarks measure like inlining versus not inlining?
So, like I mentioned on why the first benchmark is meaningless, many benchmarks see optimization as the enemy, right? But when you say that the cost is the loss of inlining, you're ignoring the very first problem with the first benchmark, which is if you can inline, it means which function you're calling, which means it is not a customization point, which means what business have you had making it virtual in the first place? With that said, compilers today are very good at devirtualizing, of figuring out, yeah, it's a virtual functions, but at this particular point, it can only be one option, we'll call that directly. And then they absolutely will inline. So it all goes back to what I keep saying, profile. Use the design that works best for you, profile it. If it's fast enough, why would you care if there's a hypothetical faster design? You don't care. You don't care about the assembly. You don't care about inlining. You care whether the design you picked is fast enough for the task you're doing.
Cool, thank you.
Thanks for the presentation. Other side. So I do have a few thoughts on why you might be seeing the behavior you're seeing, but that...
Just one point. Is there another talk here now? Okay, sorry.
But yeah, that might be an offline discussion. But I am wondering, so you're consistently seeing behavioral differences between GCC and Clang. Have you done any assembly analysis between the code gen of the two?
Absolutely, positively no. Because,
Okay,
you know why? Because I don't care. I won't twinkle the assembly later, so that's not an... What? Okay, so let's say I do and I find something. And then what?
Well, I think then that would give you an indication of what's happening, so at least you would have a better...
I have a benchmark that simply calls a concrete function and calls a virtual function. I have verified that it indeed calls a concrete function and indeed calls a virtual function, and the virtual function is faster. I have no explanation for that.
Yeah, but it would be nice...
Let's take it offline. I will be available right now at the entrance.